saw that actually we started our journey from this point A. Then with some acceleration we went up to point B, and in this journey our acceleration energy is this, right? That is denoted by A. This is the stored kinetic energy due to the acceleration. Then from B to D, the actually deceleration phase occurred, right? And in this region actually we get the deceleration energy, and we see that using the ESC method or using the ESC criteria, we can say that these two areas, the modulus of area A1 and the modulus of area A2 should be equal, right? That should be the case. That means whatever energy was stored during the acceleration phase, that will be completely dissipated in the deceleration phase. That is the main point here. If this is the case, then again from D the journey will be from A, then again D like this, and that will be a stable case, right? Okay, marginally stable or stable. Our concern is that in this time it is not unstable, right? Now today actually we will see that we will see the limit of the transient stability. What is the limit? What is the meaning of this limit? Limit means here we can see initially our mechanical input power was PM0, and we took some increment, and then updated PM is PM1, right? So this was the increment. This portion was the increment, right? So with this increment, we can say that the system is still within the stable region, right? So it is actually safe operating point. So this increment is allowable. But if we increase it further, will it be allowable? That is the question. Okay, that's why we need to understand, or we need to determine the transient stability limit. Okay, and limit means the maximum increment that you can take here from PM0 to PM1. That will keep the system within the stable state. That will be the transient stability limit. Okay, have you got the idea? So in the last class, actually I said that this pi by 2 is our stability limit. Okay, actually that is only applicable for small disturbance case, or that is actually the steady state stability limit. Okay, but the transient stability limit is different. Okay, maybe in the last class I actually made a mistake that I said that this pi by 2 will be our limit, not like that. It will be the limit for the steady state case. That's why this is called the steady state stability. For the small disturbance region, if we go in this side, then it will be unstable. But for the transient stability limit, we haven't yet found this one. We will today calculate whether we can go beyond this or not. Okay, that is the main idea. So we can begin with this slide. This is the determination of transient stability limit, and this is one kind of application of ESC. Okay, how we will find the transient stability limit. That is the main job of today's class. So before that, we need to understand that up to how much the system can actually be in the steady state regime. Okay, that means that let's say within this increment, okay, we are gaining this kinetic energy. That means there should be sufficient amount of area here in the deceleration phase, so that all of this energy can be dissipated. That is the main idea, right? Okay, now let's try to understand the deceleration area and the acceleration area. Okay. This region, why this is called the acceleration area? Because in this region, the PM is higher than P. How? Because we are now dealing with this new PM, right? So this is our PM, this horizontal straight line. Right? And what is our P? This curvature, right? This path. This is our P. So across each point, the PM is higher than P. That means this area will be the acceleration area. Okay. Now come into this region. Within this region, you can see that this curvature represents the P, and this is than PM, right? So this area is actually the deceleration area. Okay, that means if you need, you can take this whole area as your deceleration area. Okay, but if you see that okay, after taking this much, we are getting the okay. Let me just let's say I will give some numerical example, no problem. So let's say this is the area in the acceleration phase. So the same area or energy, this is actually the energy, right? So the same amount of energy should be dissipated. Let's say all the energy have been given back within this area. That means we do not need to take the rest of the area. But we have this area in our hand. If there is any need to take this area, we can take. Have you understood this thing? Okay. Now I am giving some numerical example. Okay. At that time, these things will be clear to you. But before that, let me read out this point. Okay. So when there is a sudden change in power unit, that means the sudden change in the PM. Okay. That means from PM0 to PM1. This is the sudden change. Stability is only maintained. Stability is only maintained if area A2 is higher than or at least equal to area A1. Area A1 means the acceleration area, and area A2 means the whole deceleration area that can we take. Okay, so that means if this is the scenario, that if area A2 is at least equal or higher than this area A1, at that time the system will be stable. Because at that time you will see that there will be some D points within this region, then from D to B, then B to A, again A to B, B to D, this type of swinging or oscillation will be there. Okay, that will keep the system in the steady state, in the stable region. Okay. But unstability situation comes whenever this area A1 is higher than this area A2. Because if this is the case, that let's say here the area A1 is higher, at that time, this let's say this area A2 is lower than this A1. So all of these stored energy, acceleration energy will not be able to dissipate here completely. Right? There will be some excess energy, which will make the system unstable. How and why, that we will discuss it a little bit later. But have you got these 2 points?
Sir, shouldn't it at least be close to equal? Like if the deceleration is higher,
the deceleration phase.
Yes, sir.
Okay. We are just saying that it should be at least equal or higher than area A1. But according to the ESC method, we will take obviously the equal area. Okay. But we will see that in our hand what is the available deceleration area that we have to study. Okay. That's why this is the stability condition, that area A2 must be equal or higher than this area A1. Obviously, when we will solve the problem using the ESC method, we will take the equal area. We will not take the whole deceleration area. Okay. But this is the condition for stability. And whenever this area A1 is higher than area A2, at that time, no matter what the scenario is, the system will be unstable because all the acceleration energy can be dissipated in the deceleration phase. Okay. Let me give you some example. At that time, these 2 points will be more clear. Okay. So let me draw this picture. Okay. Again, let's say initial operating point, that is the PM0, and this point is point A. Okay, I am just redrawing this figure here, and in this time the PE0 is equal to PM0. Okay, then there was a sudden increase of this input power. PM, right? That's why let's say the new PM is here. Okay, so this is our new PM. This is the PM1, right? So this point will be P, right? So what area you will get in the acceleration phase? Let's denote this point, this intersection point as C. So your area ABC will be the acceleration area, right? And what will be your available deceleration area? It will be this whole area, right? Because in this area your PE is higher than PM. Okay. Now let's say this is 10 unit. The area of this portion is 10 unit, and this is 90 unit, right? So using this condition, our area A2 is higher than area A1. So in this case, the system will be in the stable region. How? Here this is 10, so you will go from B to T such that this area can be 10. Then from this will be D point, and from D to B, B to A like this. Okay. So we are not using the whole deceleration area. Rather than we are just maintaining this condition that if area A2 is higher than or at least equal to this area A1, at that time the system will be this. Okay. So this 10 will be dissipated here completely within this region, and from this D it will come B again A. So it will be like this. Okay. Now let's increase this PM1. Okay. So let's take another point with go on. Let's from this P. Always the increment will be from this. We are considering this is as initial point, and the step increase will be from here. That means this PM2 will be from PM0, not from PM1. This was the first case, and this is the second case. Whenever the sudden increase was from PM0 to PM2. Okay. In this case, look, the acceleration area has been increased, right? Let's say this is now acceleration area, and this portion is the deceleration area, right? Let's say this is 40, and this is 60. Okay. If this is the case, here as well the area A2 is higher than area A1. So this is the condition for stability, right? Because this 40 we can, let's say maybe the T will be here, this will be the T. So this we can dissipate this 40 unit energy within this area, right? Then from this G to B, then B to A, that will be the swing. Okay, the system will be within the stability.
So that means we can go beyond 5.
Yeah, we can. Okay, that conclusion we will say later on. Okay, obviously we can go beyond pi by 2 for this transient stability. Okay, but that thing is represented by this delta mass that I will discuss in the next case. Okay, so this is our case number 2, where actually our acceleration area was 40 and deceleration area was 60. So this is still in the stable state. Now let's think about this case. Okay. Let's say this case the increment is from PM0 to PM1 such that this area, this is the acceleration area. Let's say this is 50 unit. Okay. Let's say this is also 50 unit. So this is the boundary condition, right? Of this, because your area A2 can be higher or lower than area A2. So what is the boundary? Boundary is that both will be equal. So this is your boundary condition, right? Or you can say this is the maximum limit. Okay. So also in this case it will be stable, right? Because this 50 unit energy will be dissipated within this area. This area. Okay. That means the swing will be from A to B, then B to D, B to D, then B to D. This will be the case. Okay. Now let's think about the next case. Let's increase this PM a bit. Okay. And obviously this increment will be calculated from PM0. Let's say now the increment is like this. Okay. Like this. Let's say this is our PM0. So the increment is from PM0 to PM2. So now this will be the new C, right? And this will be our acceleration area. Let's say this is 60, and this area is the deceleration area. Let's say it is 40, right? So what will happen? Look, from A to B, from this journey from A to B, this 60 unit energy will be stored, right, during the acceleration phase. Now from B to D, this energy should be dissipated, right? So whenever it will come from B to D, it will cover this area. So how much energy will be dissipated? From this 60, 40. There is 20 unit extra, right? So from this D point, it will not move back, rather it will move forward with the hope that it can dissipate the energy later on, right? So it will, the rotor will come in this side, okay? Once it will come in this side with the hope that it can dissipate this extra amount of energy. So whenever the rotor will be in this side, what is this region? In this side, what is the relationship between Pm and Pe in this side? Again, your Pm is higher than P, right? P is less than Pm. So this is acceleration or deceleration. So again, whenever you will move forward from this D point to dissipate this extra energy, but again you are going to the acceleration area, which will actually which will not be able to dissipate this energy. Rather, it will actually store some more acceleration energy, right? So whether making it 0, it will be maybe 25, 30, it will also increase the stored acceleration energy, right? And from this region, it can move back. That means it is still increasing and it will go inside like this, okay? And if you plot the delta, so delta is increasing. If you plot it with respect to time, maybe you will see that this delta is continuously increasing. That is the master velocity. Have you understood this thing? So what is our limit here? Limit is this point. Okay. What is our limit? Limit is this part, right? This is the maximum increment that we can take. So because let's say here this is 50 unit and this is 50 unit. So both here this is the boundary condition, right? If we go beyond this, then we will see that the system will go to the master velocity. Okay. So now, so how we can determine the delta max? Because delta max is the maximum delta that we can take, right? So in this case, it will go up to D. So this D point is actually the delta max. So obviously, this delta max should be higher than pi by 2, and it will lie in between pi by 2 to pi. Okay. So we still don't know this value. It will depend. It will actually vary depending on these parameters. Okay. We will solve one example where we will see that how we can calculate this delta max. But have you got the idea that this delta max will be within this pi by 2 and pi, and why? Now look this point. These 2 points will be are now clear to you. Third point, the limit of stability occurs when delta max is at the intersection of line PM1 and the power angle curve. The intersection, where is the delta max? The intersection of PM1 and the power angle curve. So there are 2 intersections P and D. Which one will you take? For 90 to 180 as shown in the figure by point. Okay. That means our delta max will be the intersection of PM1 and this curve, and this intersection there are 2, but we will take the point which actually lies in between 90 degree to 180 degree. That means this point T. That will be our maximum limit. Okay. And what is the maximum transient stability limit? It is this. Okay. Because we are increasing the input power. Okay. So this increment will be our transient stability limit. Okay. Any question up to now?
Does that mean the delta max covers the same value of P as P and E?
This we will calculate this delta max now. Okay. There are some derivations for that. Okay. There are delta 1, delta 0. So how we can represent this delta max now, or how we can calculate this delta max. That will be our next one. Okay.
So is it for whatever part of PM1 when area, both areas are the same, in that point of delta max?
Exactly. That will be the limiting point at which actually these two area will be same. At that time we will take this point. Okay. The intersection of PM1 and the power angle curve. And there will be 2 points obviously. We need to take the later one that lies in between 90 degree to 180 degree. Okay. Now we will calculate this thing. At that time we will find your answer. Okay. So now the next slide. Okay. Now for this limiting case, this is our limiting case, right? Where actually your area A1 is exactly equal to area A2. Okay. So in this case, we can apply the equal area criterion method, right? So these two areas should be same. So what will be the area A1? Can anyone say what will be the area A1? This area. We calculated it previously, right? Using this formula, it will be PM1 minus P max sin delta, because this is actually the P. So this is nothing but the PM minus P, right? And the integration should be with respect to the delta, right? So, and what will be the limit? It will be from delta 0 to delta 1. Okay, to the case. This is the area here. How did the right? Actually, the same thing. This and this are actually the same thing. Okay? How did the right? Actually, they calculated this area like this. How? They first calculated this whole area. This is a rectangle, right? This whole area is a rectangle. So, what will be the area of this rectangle? This side multiplied by this side. So, this side is 0 up to PM1. So, that is actually PM1, right? And what is this value? The difference between delta 1 and delta 1. So, delta 1 minus delta 1. Okay. So, this multiplication of two sides of the rectangle will give you the area, right? This is the whole area. Now from this area you need to subtract this whole one, right? Then you will get the acceleration, right? So what will be this area? This area is under this curvature, right? The P. That means this area will be nothing but the integration of P with respect to this P with respect to delta, and from delta naught to delta 1, then you will get this area. Can you recall this thing from your intermediate knowledge?
Yes.
That the integration of this between these two will give you actually this area, right? This area. And if you subtract the square rectangle area from this area, then you will get this expression. Okay, this is the case. Also from this line you will get the same thing. How? We can separate it, right? It will be PM1 P delta. It will be delta naught to delta 1 minus this thing P max sin delta D delta, right? So same limit. Look, what will you find here? After the integration, it will be only PM1 is the constant one, right? You will get the delta. If you set the limit, it will be delta 1 minus delta 1, right? So you will get PM1 delta 1 minus delta 1. The next parameter is this. Can you understand this thing? This is simple mathematics. Okay. So using this, you can find the area of A1. Okay. If you don't understand, you can ask. Okay. Do not hesitate to ask. Now, this is area A1. So what will be the area A2? Can anyone say how they write it like this using the same concept? Can anyone say? This is which area? The first term? The area under the P curve, and from delta 1 to delta max. That means the area under this curve, this whole area. This is represented by the first term. Okay. Then if you want to get only area A2, then which portion you should subtract?
Rectangle.
you should subtract this below rectangle, right? That means let's say the blue one, this one you should subtract, right? So what is the area of the blue one? It is again the rectangle. So this is PM1 and this side is delta max minus delta, right? So you will get the area of this blue one and this is the area of the other one. Then you will get area A from this expression. Okay. Then complete the integration of this. Now complete the integration. If you change the sides of some parameters of some terms, you will get finally this thing. Okay. Do I need to show this thing? I think you can calculate it by your own, right? You have to just do the differentiation here. Tmax is the constant. So sin delta will be, after differentiation it will be minus cos delta, right? It will be minus cos delta, then you have to place the limits. Then in this side also minus cos delta, then place the limits. Then change the sides. Then finally you will get this thing. Okay. Then you can substitute this Pn value with this. How? Because our target is now to find this value, this delta. Okay. Now in this thing, this we can replace this Pm1 by Pmax sin delta max. How? This is Pm1. In this point T, the Pm and Pe are equal, right? In this point, this P and Pm1 are equal. So what is Pe here? It is Pmax sin this angle delta max. Okay. Okay. If I say that, what is the Pe here? So you will write Pmax sin delta. But which delta? This delta. That is delta 1. What is Pe here? The Pmax sin delta 1. So what is Pe here? Pmax sin delta max, right? Because this P is the function of delta. And in this point, your P is exactly equal to Pm1, right? So you can replace the Pm1 with this Pmax sin delta max. Okay? Then you will get this expression from the previous equation. This will be your expression. Okay? Now from this equation we want to solve delta max. But by looking at this equation, you can see that this is not pretty much straightforward to solve delta max from this equation. Because there is some non-linear term here as well as here. Okay? So actually you can't write like this. So it will be some parameter here, you can write like this. Okay? Or actually you can't be able to get any analytical solution. So you need to take help of the iterative techniques. Okay? So there are many iterative techniques. We will use the Newton-Raphson method. Okay? For this expression, we will use the Newton-Raphson method and we want to find the value of delta max. Okay? So now go to the any question up to now? Right? Now how we can solve the delta max using the iterative technique? Okay? That is important to understand. Okay, first we have to write this expression in terms of the function of delta max. Okay, so that means the left side, look, here we have the delta max, here also we have the delta max. So the whole left side is actually the function of delta max, right? And the right side will be only the constant c. Why this is constant? Because this delta naught is the initial point. This point will be given in your question. You should know this point, right? That from where you study your journey, it should be known to you. So you know this value, so this should be constant. So this expression can be written like this. Okay. Okay. Now, okay. What is the step for Newton-Raphson method? The first step, you have to make some initial guess, right? You have to make some initial estimate. Here you can make some intelligent estimate. How? You already know that this delta max will lie in between pi by 2 to pi, or from 90 degree to 180 degree. So obviously you will take the initial value in between this, right? You can take below this, no problem. At that time your number of iterations will be higher, right? You will need more time to reach the convergence. But if you take the estimate properly or intelligently, at that time your convergence time will be lower, right? So this is the first step. You have to start with an initial guess. Let's say that initial guess will be your delta max, and this is for index k. Okay, or let's say this is the first value of delta max. That's why this is delta max. That's 1. Okay, you know the delta max 1. Let's say you have started with this value. Let's say this is you have taken it 120. Okay, what is the next step? You have to apply this Newton-Raphson algorithm formula. What is the formula? You need to know the del delta max, because okay, why? Because when you know this del max 1, right? So what will be your del max 2? It will be your previous del max plus the increment value calculating from the previous iteration. It will be like this. Okay, that means you know this value, but you don't know this increment. You should calculate it. Okay, so that means this is index k, this is also index k, right? This is the delta max. What will be the formula? This is the formula. I think you have already studied it in your power system 2 course. Okay, whenever you solve the load flow using this Newton-Raphson method. Okay, so it will be c minus f of delta max. That means what is c is? What is this thing? The left term, this overall left term, right? And you have to calculate this thing at delta max k. So this delta max k is known to you, right? It is known to you because this is your initial guess. So you can calculate the f of this delta max k term. Can you calculate it? Are you with me? So I am saying that to find the del delta max of k, we need to know all the parameters in the right side, right? So we know the c. How? We know the delta naught value. So cos delta naught will be c. So how we will find the f of delta max of k? We know the delta max of k because this is our initial case. Let's say this is 120 degree, right? So place that 120 degree here. Then you will get this point because you know the delta naught. If you know the delta max initial value, put it, you will get the f of delta max evaluated at your iteration k. Okay, then you will get this value, the upper term. Have you got this point? Okay. Now actually there is one interesting thing here. I don't think that whether you have noticed it previously or not. Why this expression is like this? Okay, look from here. I am just giving you the internal working procedure of this Newton-Raphson method. Okay, how actually this works. What is this thing? Look, this is this equal to this. That means your c minus f of del max should be equal to 0, right? So whenever you will reach to the optimal point or the actual point of delta max, this term should be 0. If this is 0, what will be your increment? There will be no increment. Means that you are at the actual value. Have you got the idea? But as this is the iterative technique, it is quite impossible to find the exact 0, right? So what we normally do? We take some tolerance, right? Like this. If this value is within some tolerance, then we can allow that value like this. Okay. That means here always it is trying to minimize these two gaps so that our value can be closer to the actual value. Okay, that is the working principle behind this Newton-Raphson formula. Okay, then what is in the denominator term? It is the differentiation of this function f with respect to the delta max, and that should be evaluated at this delta max k. Okay, so how can we calculate this? That thing has been written over there. This over this it will be simply this. How? Just differentiate this term with respect to delta max, then you will get simply this thing. Okay, let me just show the differentiation here, then you will understand it better. Okay, so if you differentiate this term, okay, let's first multiply this and elaborate these terms. It will be delta max, okay, sine delta max, right? Then minus delta naught sine delta max plus cos delta max. Okay, differentiation of this with respect to delta max, right? So this is the left side term and this is actually your f of delta max. That you should differentiate with respect to the delta of delta max, and you need to evaluate it at delta max of k. Whatever value you put your hand at that iteration, you have to evaluate that thing at that point. So first differentiate it. So what you will get here, the delta naught will be constant. Okay. Here there are two terms, both are the function of delta max, right? So which rule you will apply? You will apply the UV formula, right? This is U, this is V. So what is the formula? It will be U. U means this delta max. Then the differentiation of V, that will give you cos delta max, right? Then the plus next term V is the sine delta max multiplied by the differentiation of this, that will give you 1. Okay, minus this delta naught sine delta max, sorry, this is minus delta naught cos delta max, right? Cos delta max, and the differentiation of this will give you minus sine delta max. This and this will be cancelled out. This is cos delta max, this is cos delta max. If you take common, it will be cos delta max multiplied by delta max minus delta max. Okay, that thing is written over there. This is the differentiation of this f. Okay, delta max minus delta naught cos delta max, and you have to evaluate this differentiation at delta max k. So put this 120 degree the initial value here, you will get the result here. Then you will get the delta max of k. Then you need to calculate the next delta max, that is the k plus 1. It will be the previous delta max plus the previous input. Okay, then that will be your second term, let's say k plus 1. Then again you will calculate the del delta of k plus 1, max of k plus 1 using this formula. Now in this formula it will be k plus 1, it will be k plus 1, right? Then you will calculate it. Then from here you will calculate delta max k plus 2, sorry, delta max k plus 2. It will be this plus 1 plus the previous delta max. Like this you will forward, right? Up to how much you should forward? There should be some tolerance that will be given in your question paper. If your consecutive 2 del max value remains below this tolerance, then you can stop your iteration and you can take the final solution as your best solution. That is the case. Have you got the idea? Okay. So, like this way you can calculate the delta max. Okay. Once you can calculate the delta max, now let's calculate the delta 1. Okay. Because inside the delta max formula there was no delta 1. There was only delta 1. That is known to us. Now we calculated this delta max actually, but we don't know the delta 1. How we can calculate the delta 1? We know that this is the intersection point. This is also the intersection point, right? And this is the PM1. So we can write PM1 is equal to what? Pmax sine delta 1 we can write, right? Also we can write it is equal to Pmax sine delta max. Okay. So this thing has been taken, right? This. Okay. Then how we can find the delta 1? Actually it's better if you follow, if you take the next equal. Okay. Let's take the next. Let's say this two are equal. Okay. So what will be your delta 1? It will be sine delta 1 equal to sine delta max. and you know the range. These two values are within 0 to pi by 2. So what will be your delta 1? It should be the complement of 180 of delta max. It should be pi minus delta max. Have you understood this thing? That means, let's say if this is 20 degree, it should be 160 degree. The summation of these two should be 180 degree, because the sine 20 is exactly equal to sine 160. Sine 50 should be exactly equal to sine 130. That is the case, right? So how we will write this thing? The value of delta 1 from this expression, you can write delta 1 simply equal to pi minus delta max. Have you got the idea? Is it confusing? So actually the summation of this delta 1 and this delta max will return you this pi. That is the case for this side. For any, if you take PM1 here also, this will be the delta 1, this will be your delta max, and the time to delta 1 plus this delta max will give you the pi. So for any value of this PM1, you will find this relationship, that your delta 1 will be equal to pi minus delta max. Okay.
So graph থেকে জিনিসটা বুঝছি ইকুয়েশন থেকে sin delta 1 equal to sin delta max টি লিখছেন, তারপরে স্যার পাই জিনিসটা কিভাবে আসবে?
Okay. This is some trigonometric step you can apply here. Like look, this is sin delta 1 equals to sin delta max, right? So you can write it as like this. Sin delta 1 is sin, let's say, you can write it like, okay, let's say this delta max, you can write it like, not actually pi minus delta, you can write it like this, 360 plus delta max. It will be the same, right? Okay. Then how we can solve this thing? Can anyone say?
স্যার pi by 2 এর যোগ গুণিতক নিয়ে মাইনাস pi del max করে না
স্যার আমাদের সাইন 180 ডিগ্রি থাকে বা 90 ডিগ্রির যোগফল থাকে মানে চেঞ্জ হবে। সো আমাদের সেকেন্ড কোয়াড্রেন্টে সাইন পজিটিভ, যেহেতু সাইন delta 1 পজিটিভ, সো সাইন delta
You can take it like right, sin
pi
pi minus delta max, right? Yes, you can write it like this, because it will be actually the sin delta max, because it will be the even multiple of 90 degrees. That means it will be
sin
sin will be sin, then we need to take the sign, whether it is positive or negative, and this angle remains in this quadrant, right? So in this quadrant, sin is actually positive. So we can write it like this, okay? So now you can cancel the sign, it will be delta 1 equals to pi minus delta x. This will be this. So have you got the idea that your delta 1 will be pi minus delta x, okay? So then we have example 11.4a and 11.4b. Okay, so this will be your home task. Okay, you will solve it by hand calculation. Okay. Okay, not now. Actually, in the next class, I will solve the example 11.4, and I will show you the process how you should forward. Okay, move forward. Then you will be able to fill up this table with your hand calculation. Because in your exam, this type of question will come, right? So you need to calculate these things. Your target is to calculate this delta max, and for that one you need to know the, let's say this is your initial case, right? Then whenever you want to know this value, you need to know the value of this plus this. Sorry, not this plus this. You do this, right? Then from this you will calculate this. Then the next value will be the addition of this plus this. And in each step you will check the difference. If it remains within your tolerance, then you will stop. Maybe this type of problem you have solved in your lab, right? Can you remember?
Yeah.
Maybe in your lab one you used to solve this type of problem. That in this step you have to calculate this thing. So I will show you the steps. So whatever we have learned here, the derivations and these equations, this thing will be needed to solve this example problem. And after that, you can solve it by your own. Okay, this example, because you will face this type of example in your exam. Okay. So this topic, sir, will be discussed in this class. We can start in our class.
For neutron reduction method, sometimes the solution doesn't converge. Will that be an issue?
Yeah,
Sometimes in neutron reduction, the solution doesn't converge.
actually, first of all, in the first step, you are making some guess, right? Obviously, you will make the guess within this pi by 2 to pi. That is the important point. If you take it, maybe you will converse very good. I think you will converse. There will be no much problem because there is only from here to here. So if you take some middle value like 120 or 140, then within 5 to 6 items you will get the tail next one. Okay?
Sir, আমাদের এখানে একটা লাইক রেক্ট্যাঙ্গুলার পোর্শন আছে যেমন এক্সিলারেশন নিয়ে এটার পাশে একটা রেক্ট্যাঙ্গুলার পোর্শন এই এর যে এই স্যার এক্সেস এটা তো একটা এক্সেস দিস ইজ দ্য বাম পাশে দিস ইজ
Why we are not considering this? Look, initial point was this. Then we are going here. So from A to B, what should be our area? This. The intersection between PM1 and this, right? Okay, but we are not considering this because this was from 0 to A. We assume that our initial point was A, then we are operating it from A to B, B to B. We are not coming to this 0 point. That's why we are not.
এক্সপ্রেশন এনার্জিটা আমাদের কোনো কন্ট্রিবিউশন নেই
No. If you take it from here, you know then it will be the acceleration area. Because in this region, it is here also your PM1 is higher than your P, so it will be acceleration energy. But as you are considering your journey from point A, that's why you will not get this acceleration energy in the calculation.
স্যার আমাদের উপরে একটা এক্সপ্রেশন আছে বাট যেই অংশটা হচ্ছে আমাদের কাটার নিচে ওইটাকে আমাদের লাইক আমরা যখন পিএম বাড়াই দিচ্ছি তখন আমাদের পিএম এর একটা পোর্শন হচ্ছে আমাদের এক্সিলারেশন করে দিচ্ছে আর কিছু অংশ হচ্ছে আমাদের মানে মোটর বা আমাদের জেনারেটরকে অ্যাবজর্ব করতে এই নিচে পোর্শন আমাদের
Actually, only this area, where actually this curvature of P will be in the upside of this PM1, that is your deceleration area, deceleration. Other areas, this area, all this area will be acceleration. Only this and this area, this and this area also, this will be your deceleration. Okay? Because you need to think the intersection between PM1 and P. If PM1 is higher than P, that will be acceleration. If PM1 is lower than P, that will be deceleration. At that time, you will get only this type of areas. This area as your acceleration, then this as your deceleration, again this as your acceleration. You do not need to take these areas. These are not the effective energy. Because always you need to take between PM, the difference between PM and P. Yeah. So this should not be in your calculation because you are taking the difference. So any other question?